Get to that next. Okay. Okay, so here we go. So with this idea of this mass defect, what scientists discovered is they discovered that when you take individual pieces of an atom and put them all together, that missing mass is converted into energy. And that energy is what holds an atom together. Okay, and this is actually where we get the famous equation of E equals mc squared.
Oh my gosh, thank you.
You're welcome. I know, it's an equation you hear all the time. They throw it out there.
I committed myself. I was like, well, Denise, you'll just go to school until you learn what E equals mc squared means.
Wait, are you going to stop school now?
No.
Okay.
That's what kept me going for a while.
Good. So write that equation in the box. And then underneath it, it might be a good idea to define your different terms. Okay? So E is our energy, M is the mass defect, and then C is the speed of light. So we won't use calculations with this equation, but what I want you to understand is this right here. That even if I have a tiny amount of mass, so if M is really small, look what we're squaring. How big a number is this? And then we're squaring it. So even though the mass can be tiny, the amount of energy that comes out is insane. Okay? All right, so with this mass defect, okay, what it is it's releasing the energy that binds the nucleus together. So often you can think of this as, we call it the binding energy. The energy that holds a nucleus together. Because otherwise, normally a nucleus, I don't remember if it was in this class or not, somebody once asked, wait, if a nucleus is just positive things and neutral things, what do two positive things do to each other? Yeah, they repel. So what keeps the nucleus from just falling apart is this binding energy. There's a force in there that holds the positives in. Okay? Okay? So what we get here is the energy that is released from the nucleus comes from these things called nucleons. Okay? A nucleon is the fancy name for everything that lives inside the nucleus. So anything inside the nucleus you can call a nucleon. So after you write that definition down, pick up your periodic table in front of you. Okay? And then what I want you to do is don't say a single word, but answer this question. If that's what a nucleon is, which subatomic particle is not a nucleon? Assignment. But if you picked C, you are correct. You can have a smiley face. And then can somebody, by raise a hand, help us know why? Why is an electron not a nucleon, Denise?
Well, because electrons are... Well, because like a nucleon lives inside the nucleus, and we know that the nucleus is mostly made out of like protons and like... Yeah, right?
Uh-huh. Yeah, very good. Yeah, so when you look at an atom, the nucleus is just the protons and the neutrons. The electrons are outside. So once again, core idea of this entire unit. When we're talking about all these things, these little guys are just orbiting. They don't have anything to do with what is happening. It's all about what's happening inside here. Okay? So then E is that binding energy that's holding that nucleus together. All right, so what we get here is that the higher the binding energy, the more stable a nucleus is, right? Makes sense that the more force there is holding it together, the more stable it will be, right? More glue, more stable. So this is what it means when an atom is radioactive, it's because its nucleus is unstable. And this is where I wish I had a button to start playing Imagine Dragons at that moment. Did it come to anyone else's head when I said radioactive?
Yeah.
Okay, so an unstable nuclides make it radioactive, and then it's going to undergo what's known as radioactive decay. So when I say something is radioactive, does it have anything to do about its electrons? No, it's all about that nucleus and that it is unstable. We'll define what that means as we go. All right, so the next thing we're going to talk about today is there's a little table. Everyone see that, right? Is that where we're at on our notes? Okay, so we're going to talk about the different types of radiation. Okay, so when somebody says radiation, it's a broad term, and there's different things that can come out. Okay, so the first type of radiation is known as an alpha particle. Okay, so that right there is the Greek symbol for alpha. It kind of is an A, but it's not technically an A. To be honest, when I write alpha by hand, it's a fish. That's an alpha sign. Yeah. That's the computer way of typing it, but okay. What an alpha particle is it's a helium nucleus. That's what it's made of. Okay? So then the symbol we get for it is this, 42He2+. So that is our chemical symbol. So whenever you see the word alpha particle, it's talking about one of these. Okay? So it's been a while since we've looked at these symbols, so let's review really quick and fill in the other parts of that first line. What does this top number right here represent? The mass. Good. So we know for an alpha particle, so that next column, the mass of an alpha particle is 4. What's this bottom number? Good. It was like the atomic number or proton number, right? Which makes sense that helium has 2 protons. And then the charge, of course, is +2. Okay? The next part on your chart says penetration power. What does it mean to penetrate something? Intrude, go through it, right? So this is how strongly can this radiation pass through things. For alpha, when we talk about bad radiation, it's not the alpha particles.
So it's like very weak.
Yeah, you can put weak or low in terms of its penetration power. If you want to maybe put like paper in parentheses to remind you, right? Because really, if it can't pass through paper, can it pass through your skin? Probably not, right? Most of the time what happens with an alpha particle is because it's a helium nucleus, is it just finds 2 electrons, steals them from somebody, turns into helium, and floats up into the atmosphere. Right? And that's about it. Okay? So very, very low in their penetration power. All right, our next type of radiation is a beta particle. So the Greek symbol for beta, it looks like a B, but it kind of has a little tail on it. So it's like a fancy B with a minus. And what it is in terms of a particle is it's an electron. Okay, and stay with me on this one because it gets a little bizarre. Okay? So a beta particle is an electron. Okay? So its symbol is 0, -1 E, and keep in mind it's a lowercase e because that's how we write electrons. And then we put a minus sign. So with this symbol, what's the mass of an electron? 0. Is it really 0?
No, that's like 0.004.
Yeah, it's so small that we call it 0. So you can just put 0 in that box. Okay? What's the charge of an electron? -1. Okay, wait a second. Didn't I just say that we're not talking about electrons?
Yeah.
Yeah. So it is an electron, but when we get to it, it's not an electron out here.
Electron inside.
So with the beta particle, so now this is in the medium range of penetration. Okay, so it's stronger than an alpha, but not our highest yet. Beta particles will pass through paper. They possibly could penetrate you, and they get stopped by metal. That metal has the ability, dense metals have the ability to stop beta particles. Somewhat, yeah. Yeah, I think X-rays would fall near that, in that same comparison, for sure. Yeah. Okay? All right, our next particle is known as a positron. And it is just a positron, so its name isn't different than what it is. Right? So it's a positron. So notice it's the same symbol, but now a plus sign. So this is going to get really weird, and you just got to hang with me because I promise we'll clear it up. Okay? So the symbol for a positron is it's a positively charged electron. I know, which is weird because we've always talked about electrons and that they're negative.
Wait, it's an electron?
It's an electron that's positive.
Wait, okay.
Yeah.
Wait, so where is the beta particle?
Like in general?
Like where, like, is it, you said it wasn't in the,
So it's in the nucleus.
oh, okay.
Yeah. And when we talk about, so these are like the types of radiation that can come out of a nucleus. Yeah. Okay. This one, a positron, is on the same level as a beta particle in that it's in that medium category of penetration. So does anyone notice a connection between why would these two be better at penetrating than an alpha? Do you notice something like maybe with the symbols that would show you that?
Because they're smaller?
Yeah, really, if you look at it, an alpha particle is a lot bigger and heavier than these guys, right? And the smaller they get, typically the better they are at penetrating. Which is why our last type of radiation, gamma, okay, so this is the Greek symbol for gamma.
Just a Y?
It's a Y, or if you're doing it the fancy way, it's like, oh, that was bad. Don't draw that. So it's like a downward swimming fish, is the way you can think about it. But when you look at it outside, it kind of looks like a fancy Y. Okay? All a gamma is here's the symbol for it. Oh, not that. That. So what do you notice? Does a gamma have mass? No, because the top number is 0. Does it have any protons? No. So the thing about gamma is it's just pure energy. So it doesn't have a charge either. But because it's so high in energy, that's why it has the highest penetration power.
Wait, so does like lead stop it though?
So in order to stop gamma, you need some sort of thick combination of lead and concrete. Now this kind of goes to what Brock was leading into of like, so we have these types of different radiation, which means these things are leaving the nucleus to make it stable. So our next big thing for today that I want you to understand is what happens to a radioactive atom once it releases radiation. Okay, the whole key here, so first off, is we always compare the radioactive thing, the vocabulary word. All right, so look at our numbers here, everybody, and take it piece by piece. So if I have a uranium atom and it has a mass of 238, the arrow means it's changing. It's basically kicked out an alpha particle. So if it had 238 and it kicked out 4, then this thing must be 234. And you can always check it by working back, right? So 4 plus 234, yep, that equals 238. So now focus on the bottom number. If this is 92, has 92 protons, and it kicked out 2 of them, how many are left? 90. All right, now here is the final piece. If it only has 90 protons, what is it? It's a new element. So look on your periodic table, find number 90. What has our uranium actually changed into? Thorium. So when something undergoes radioactive decay, it actually changes into a new atom, all on its own, because it's trying to get more stable. Okay?
What happens if it like decays into another radioactive?
Then that thing will then keep decaying. So we have certain decay series where it'll just keep going and going and going and going until it gets stable. Okay, so our next one is a beta emission. So follow along with me here. Okay, focus on the top number. 131. It kicks out a beta particle. Does the mass change? No. So the mass doesn't change. But now be careful with the bottom number, okay? Think of your arrow as an equal sign. Okay? So this says 53 equals something plus -1. So what plus -1 gives you 53? 54. Good. Don't be tricked because the number actually goes up. Okay? Which means what element have we created? Xenon. Very good. Okay? All right, try this next one. Try the positron emission. Try that one on your own. See if you can fill in that box, then we'll check it. So focus on the top number first. In this case, with positron or beta, does our mass ever change? No. Because it's always 0. So that stays the same. Then we need something plus 1 equals 19. So it would be 18, which means its element argon. Everyone look at the periodic table, okay? So look at the bottom numbers here. So this is a key theme. Your mass number up top may not match what's on here. The proton numbers always will. Because do you remember where this number comes from?
The average of all.
It's the average of them. Yeah, so that's a great observation, because if you try to find something by its mass, you're going to get confused. Because, yeah, it sometimes doesn't. Like, xenon on here is what? 131. But iodine is technically 126, right? But that's just because they're the average of them. Which shows you why this one is probably radioactive, because it's not close to the average.
Okay.
So, good observation, because always go by the proton number, because the mass is averaging. Okay? All right, our next one is an electron capture. So notice the difference here, that the arrow is now after. So an electron capture is the process of a nucleus actually pulling an electron into the nucleus, is an electron capture. Okay? So once again, the mass doesn't change. Still 106. But now we have 47 plus -1, so it would be 46. Good. So when it pulls that electron in, it goes down and we get element palladium. Okay. All right, before we talk about gamma, go back to your little table on the front. What is the symbol for gamma again? Y, and what are our two numbers?
What?
The two numbers that are with it. 0, 0.
Yeah.
So is this going to change anything mathematically? No. So we actually won't really worry about, in a sense, balancing gamma ones. Just understand that they are there, and it's often a part of other ones. So when something does beta, it also may be kicking out some gamma. We don't see it in terms of a mass or a change, but it could be coming out as well. So hypothetically, you could have like, that could also be there. We won't worry about writing it in because it doesn't change anything, but recognize that it is there. And then the word for all of this is known as transmutation, where it's a process of one element actually turning into another one. So transmutation is the process of one element actually changing into a different one. So this is why, or in a sense, we'll define more for Brock what it means why a nucleus is unstable. So what makes it unstable is the ratio of protons to neutrons. So if you look at our graph here, this red line is the line of stability. If atoms are on the line, so if an atom has 40 protons and 45 neutrons-ish, it's stable. But if I have an atom that has 40 protons and only 20 neutrons, it's not. So then they are going to be radioactive and find their way to the line, depending on alpha, beta, or capture. So that is why they're radioactive, is they're trying to get to the right ratio of protons to neutrons. And we'll watch a little cartoon here in a second that I think does a good job at kind of visualizing this instability thing. Okay? All right, try those practice problems for me. When you have them all answered, put your pencil down so I know you're ready to talk about it. So, all right, check your answers up here. If they don't match mine and you don't know why, let's talk about it. Otherwise, you can have a smiley face for everyone you got right.
No.